So suppose that x and y are functions of time. Okay, we're not given specifically what they are, but we just know that as time changes, these two guys change. Okay, and that the point xy moves on the circle given by the radius of 1 centered at the origin. Okay, if x is increasing at 1 centimeter per second, what is the rate of change of y when both x and y are equal to root 2 over 2. Now I rationalized their denominators for these, but you can leave them the way they were. It doesn't matter to me. So what we've got here is the circle. I'm going to draw that guy out for you, just so you can get a picture of what's going on. We've got a circle. It's centered at the origin, and its radius value is length out. This length out here is 1 unit. And this is all given to me. So this is 0, 0. This information is all given to me by this guy right here. So what I'm going to do is I'm going to take the rate of change of this whole thing with respect to time. Because what we want to find is what is the rate of change of y with respect to time. So we want, how does y change as time changes? Meaning, as our point is moving along the circle here, however it's moving, okay, and it's at exactly square root of 2 over 2, comma, square root of 2 over 2, 45-degree angle. Okay. At this exact point, how is the y value, the height, changing? Okay, so as it moves, let's just assume for a second that it's moving in this direction. Okay, and actually, it's not. The x value, x, is increasing 1 centimeter per second, which means that this length right down here, is increasing. So y should be decreasing. Now the question is, how fast is it decreasing? So this is what we want. How is y changing with respect to time? So what we've got is our original equation, x squared plus y squared is equal to 1. And we're going to take the rate of change of this whole equation with respect to time. So that would be d dt of x squared plus d dt of y squared is equal to d dt of 1. Now, I'll show you in a second. There's another way to look at this, but this will get us where we want to go. So d dt of x squared, well, we use the chain rule here. We know that x is a function of t. So what we want here is dx dt, how does x change with respect to time, times d dx of x squared. Now we'll do the same chain rule right here. So this will be dy dt times d over dy of y squared, and d dt of 1 is 0. So this right here becomes 2x times dx dt plus, this becomes 2y times dy dt, and that's equal to 0. Well, what we want is how does y change with respect to t. So let's go ahead and solve for that guy. So that gives me dy dt is equal to negative 2x dx dt over 2y, which is equal to negative x dx dt. Oops, I wrote dx dx here. Sorry about that. It's force of habit there. So dx dt over y like this. So this is what dy dt is. This is how y, this right here, this guy right here, is how y changes as t changes. Okay, that's what we're looking for. Now, but this guy right here, the x and the y variables, okay, that's our x and our y right here. So this is equal to negative square root of 2 over 2 over square root of 2 over 2 times. Now, what is dx dt? Well, this little guy right here is how does x change with respect to time? And we know that it's increasing, so it's positive. It's 1 centimeter per second. So this is going to be 1 centimeter per second. We'll assume that these guys are in centimeters, but this is going to cancel out. And so these guys go away. I'm left with negative. So this would be negative 1 centimeter per second. That's dy dt. So what we've got here is y, our y. Now if you graph this guy out, here's what's going on, guys. If you look at that part of the circle, here's our point at a 45-degree angle. Okay. X, its x length. Okay, let me just box this guy out here, and I'll do it in different colors. This is the x, the change in the x with respect. Actually, I should write it like this. dx dt tells me as time changes how this guy changes. Well, it changes its length. The amount of change is going to be 1 centimeter per every second. Okay. Now, if that changes by a centimeter in a second, okay, then the question is, this point goes from here down to here in a second. So the question is, what is the change in the y? So this length right here, this length right here is the change in the y with respect to time. And so this length right here is negative 1. We went down 1 centimeter in that second. So right here, okay, that tangent line tells us the instantaneous change. Now remember, this is as we push up, okay, this would be, this guy right here would be the actual value. This right here would be a linear approximation, okay, because it would actually change by a little bit more than that. But exactly at square root of 2 over 2, common square root of 2 over 2, the rate of change of y, this guy right here, with respect to time, is given by negative 1 centimeter per second. Now another way of doing this, like I said, is to just go directly and say, well, dy dt, okay, that's going to be equal to, well, let's not do that. I don't want to confuse you. So let's just stop there.